Thought I hit, oh, maybe I hit Windows on. Okay, so we're recording. So those problems are due today. I've got it from 3 of you, but from 2 of you guys who aren't here, this is not acceptable to be late.
Are you going to be going over these problems at some point? Because if so,
yeah, we're gonna go over them now.
Okay.
Which is why they're due, right? I can't go over them if.
No, I was just wondering because I didn't get anything, so I wanted to know which problems they were.
Oh, didn't I send you the Unit 2 notes? They're in there.
Okay.
So what's the first problem, guys?
I believe it was the one where you have to
So
for.
Go ahead. Go tell me the numbers, and then we can open up the book.
All right. 319.
Okay, 319. So we'll start with that one. Although if that's the
Venus one.
Yeah, I don't think I need to do that. That should have been pretty straightforward.
Yeah.
Okay, what's the second one?
320.
320, about the virtual temperature correction?
Yes, it looks like it.
Okay, so let me get together. Oops. I wish my camera didn't always bleach me out so much. It's like I got no light on in the room. I have all my shutters closed, and I'm just white.
You just have a natural glow about you, Paul.
Yeah, that's what it is. I'm like Casper. That's what I think.
I think it's because your camera's focusing on your background, and like that's why. Is it?
It's annoying. You would think it would have better control, but it's a crappy mic. So, all right. So let me go over here. Hold on. I'm just getting my stuff together. So I don't think I have this one done. So what is the answer to this? Let's see what you guys did.
You want me to put mine up?
No, I got yours. So.
Oh, okay.
I can go here and go to needs grading and go to Jim Norris. This is how long it takes me to load a document every time I try to grade a lot of stuff. It's annoying. So we have all the stuff in here. There's the worksheets, and here's some of the problems.
Mine are numbered. Keep going. There's 19.
319, 320. Okay, so given that the air is 1% water vapor, okay, so we have, for the virtual temperature correction, we're going to use what formula? What formula will we use? So everybody check in your own notes so that you got it, right?
The ideal gas law.
I ended up using
I don't think you need that.
I think I did the.
Where P is equal to density times RT?
So what you did is you eventually got a relationship between the virtual temperature and temperature as a percentage, and then you plugged in the molecular weights of one with 1% water vapor, so that's kind of good. Virtual temperature to the temperature, and you got 1.038.
Yeah, I think that's where.
You're talking about temperatures that are in the 300 Kelvin range, or, right? You're only talking about a degree, because 3% of 300 is about 1. or 0.3%, 0.4% of 100 of 300 is 1. So the other way that you would have used is what formula could you have used?
360. TV equals the 1 plus the 0.61 times the mixing ratio is what I used.
So, right?
Mm.
Could you have used specific humidity? Because what is the problem asking you to do? The problem is saying if
It's looking for the
1%
correction.
of the volume of air, so they're saying by the volume of air, you've got 1% is water vapor.
Right.
So you would say that 1% is the number of molecules, right? You wouldn't say it's 1% is the mass, but you'd say 1% of the air is the number of molecules. And then you'd have to convert mass or the number of molecules into, let me say this right, you have to convert the number of molecules into mass to be able to use the mixing ratios. And that's why you need the ideal gas law. So what Jim did here is he said, okay, find the pressure using T in the virtual temperature. So this is the equations. One of them is RdTV. The other one is RV of the temperature. And he set up this little ratio of one to the other. So that's a really interesting way of doing it. But you could have done it different ways too, but this is a really cool way to do that. But again, the key thing to this equation, to this problem to solve, is this thing right over here.
Yeah.
Hey, James.
Hey.
Hey, why didn't you turn in your assignment?
Oh, God, I got really logged down with other assignments. I totally forgot to turn it in.
Do you see how difficult it is for you to be watching the answers and then still for me to accept the assignment?
Yeah, I can leave if that's.
No, just don't take any notes
All right. Let me
on this
toss
stuff.
that in there.
So then you'll have to go back and rewatch it again.
All right. Let's toss that book aside.
Nick, did you do it this way, or how did you do this problem?
I approached it with it and with the mass. I guess I really didn't consider thinking of it as the volume, even though it said it comprises 1% of the volume. So what I did is I kind of set it up where I was plugging it into that that temperature correction. What was it called? 3.60, that equation where you set it equal to T1 plus the percentage of the mixing ratio.
Okay. Hold on.
And
Would
what
you
I
read for an
ended up,
answer?
and then I started solving for whatever the mass of the water vapor was, the 1% of that, whatever the molecular weight is, plus the, should you just pull it up? It would be easier to.
Yeah, I'll take a look at this. I want to
Okay.
show you something here. That the density is the number. It's the number of molecules plus the air molecules times the molecular weight of this sample.
Mm-hmm.
I shouldn't say W, so I'll just say the molecular weight. And I'll put that just so we're not getting confused. Of this sample. Well, I don't know the molecular weight of the sample. What I would have to do is do a percentage of them. So like you did with Venus, you'd come up with the molecular weight, and you could do it that way. And then this would become, then the density here would become mass of the sample over volume.
Mm-hmm.
Right? And that's where you're getting the density.
Yep.
The other thing that I'm assuming that you could work through is you could figure out a way of determining the mass of just the water vapor if 1% of those molecules.
Yeah, that's what I was doing.
Okay, so that's what you did. Okay, so
Mm-hmm.
let's go to needs grading, and I can go to, oops.
So basically then what I need to do is just convert it considering the density so it's considered 1% of the volume basically.
Yeah.
Okay.
I mean, this one is a more of a theoretical problem.
Mm-hmm.
So let me zoom in. Well, actually, let me go to the.
It's just the
So these
yeah.
are notes and everything too. So
Yeah. 319 and then 320.
okay.
There you go.
So you use this equation
Mm-hmm.
where
Basically I did it on the
well, this would be very similar
mm-hmm.
to what Jim did, except your molecular weight of the vapor itself or the molecular weight of the sample. See, where did you get 29.75? Is that this?
Okay, I think I probably did that wrong because
Well, here, this is what you did wrong.
yeah. Because I calculated
Where did
as
this number 44.013 come from? You guys take a look at this. Where did he get that number?
I'm trying to actually remember where I got that from. I think it was supposed to be the I don't know where I ended up actually getting that.
This one,
I must have maybe have just been
Oh, that's way
maybe I
off.
just wasn't focused on something and I accidentally plugged in the 44.013 and I never really noticed that I did that.
I think that sounds like 44 point.
Maybe I can find it. 44.013. Trying to remember what that was.
That is that the total, the average of.
You have the correct one underneath the first line, but then you just change it completely to 44, and I just don't.
Yeah,
Yeah.
I have no idea now that I'm looking at it.
You have this. Oops, you have this,
Mm-hmm.
and then you
Which
go
is what I should have plugged in.
where that is.
Yeah, honestly, I don't even remember my thought process there, but if I probably plugged that in as the 18.016, I probably would have gotten what was correct.
Right.
The only thing I can think of is that's dinitrogen monoxide.
Yeah, that's just, or maybe you came with a calculation somewhere.
Yeah. I guess probably would have been better if I would have explained where I've got that from, but I think if it was 18.016, I would get something that's a little bit more correct. It was maybe one of those things where I was calculating something and I accidentally wrote it down and
Okay.
wasn't focused enough. So if I calculate it then this way.
Now, what is the molecular weight of water vapor?
What is that symbol on the left?
Q.
Okay.
Q is, if you go to page 80 in your book, that's specific humidity. Remember this?
Thank you.
18 grams per mole.
Okay.
And dry air is 28.97 grams per mole.
97?
Yes, sir. 28, not 29.
28.97 grams per mole.
Correct.
Well, kilograms per kilomole, whatever.
Well, whatever
So,
you want to use.
yeah. So I'm trying to think here, how do I get to the 1%? Can I use this formula to do that? If I multiply by 1 over mv all over 1 over mv, what I get is 1 over 1 plus
And MD over MV is equal to W.
well,
Oh, no, it's not. My
No.
bad.
it's not W, it's mass
It's
of
the inverse. It's the inverse of
the
W.
inverse. I'm just trying to see if I can figure out a 1% with masses. The only way to do that, I think, and maybe at this point, the best way to do that is to go back to Jim's, because I think it's clean.
See,
It's a very clean way of doing it. So
see what I ended up doing? I don't know honestly, where that 44.013 came from, but I guess I just completely ignored it and still plugged in the 18.016 when I
maybe you were
calculated it.
looking at something else.
Yeah, I must have just was looking at something else when I wrote it down, plugged it in, and then,
That happens. That happens. So
yeah.
I like this way. If I feel like you would need something different, maybe you guys all say this is a good way of doing it. But all he's saying is that the temperature times the pressure times the density of the vapor times the ideal gas of the vapor times the temperature. And he's saying where P is equal to the vapor pressure. So this, he could have just said this is E. And then he says the pressure of the virtual temperature. So he's defining what temperature is, basically. Since he uses the density of, see, this is where I'm not sure I can, so here, Jim, this is the question that I have. What is this? What are you meaning by putting it here?
The density of the vapor pressure.
So it's like a partial, so
Yeah.
why is it here?
Hold on, let me see.
This is, I understand that why it would be here, but this would be the density of the dry air left behind.
Okay. Hold on.
You know what was another thing that I just saw, Paul?
Oh, go ahead, Nick, yeah?
I just saw that the molecular weight of dry air I said was 29.87, not 28.97.
That's why I put 29, because I remember that was the number that you were doing, and I don't recall it offhand.
Yeah, so, whoops. Probably could have paid more attention while I was doing this problem.
The other, okay, so this, I see this. This is all using of the vapor alone. right? That you're saying this is of the vapor alone. That's why.
Yeah.
And you're saying here's the ideal gas law using P equals rho RT. And here you're saying the ideal gas law using the virtual temperature correction. And you're saying, well, that's the same thing. So then you put it in here and you are able to get down to this box here.
Yeah. If there's another way of, there could be another way of getting there from here.
But that's a pretty interesting way. I'm not sure if that deals. You see, notice what you're missing in here. Well, sorry, that was way too fast. What you're missing in here, well, I guess you used it up here, the 0.1% to determine 28.86.
Yeah.
Huh. Interesting. That's a clever way of doing it. Nonetheless, when you go down to some of these answers, the idea of this problem is really in this scenario. Because you're not proving exact, you're proving about. And so the fact that he was able to come up with the change in the molecular weight versus the change in the virtual temperature to the temperature, those ratios, it comes out to a small number. So you're talking about a degree Kelvin. Now, that's true to a point, but when I'm up there at much higher vapor pressures, or when I'm talking about instead of 1%, maybe 4% of the air is water vapor, I'm getting like 3 to 4 degrees Celsius. So this is all predicated on this 1% of the air. And it's 1% of the volume is weird. It really is better to say 1% of the molecules. And so you could also say, here's another way, and maybe this is another way to do it, is that the vapor pressure is equal to the total air pressure times 0.101. Because if it's 1% of the mass, they're all moving at the same rate, it's 1% of the pressure. It's just not 1% of the density. Because the mass, and you could calculate that density now using the molecular weights, and you could actually figure out what percentage of the density it is, and you could do the same thing. But when you get to this relationship, that's a pretty good understanding. So this is not the best problem. I don't think that this is the thing that I'm worried about, but what I like to see is, well, what's your thought process? How do you get to answers? And that's what I'm looking for. So even when you look at Nick's versus Jim's, they're completely different. So I'm happy with watching you struggle through that and seeing what we can do. Now, what's the next problem? 3.
327.
27. Okay, let's see how you do on 327.
Oh, okay. I remember that. Yeah.
Okay. So you have this is all using the hypsometric equation. And so what we want to do is, well, let's take a look. Hold on a second. What did you get? 5? Yeah. Okay, good. So I get the answer is correct. I got the answer 53.9 meters. And he says this. So I'm going to go, yeah, that he's got the right answer. Now, did he do the right section? What you have here is the hypsometric equation for 1,000 to 500 millibars of pressure. And since we know something like that, what are the things we need to know? What was in the problem? Read. Let me hold on. My desk is not big enough for all my books.
Hold on.
Oh, they give you the mean virtual temperature of this layer. So Jim did this. Is this what is needed? Did he need to do all this stuff using the hypsometric equation? Is that what the rest of you did?
Yeah, I did that.
You used that equation? I don't think you needed to use that equation. I mean, it's totally fine that you did, but go back to page. And I just want to point this out. Go back to page 69 and look at equation 3.27. And that would have just been an easier way to do it. So that would have been that would have just been simpler. What you did is you put in the actual values of the pure hypsometric, but we already said for 1,000 to 500 millibars, we could use that equation because we know the scale height is 29.3. And then you could have gone to page 71 and look at, see in the solution on the bottom left-hand side, there's an equation.
Approximately equal 8 times the quantity P0
No,
minus.
page 71.
Oh, 20.3 times TV.
Yep. So that would have been the equation you could have just used.
Okay, hold on.
In other words, delta Z from 1,000 to 500, because all of these are, and what you did fine. You plugged all these things in there because that's what you do. That's how you get this equation. But you could have just used is 20.3 times the mean virtual temperature. We know 20.3 and the mean virtual temperature is 273 Kelvin.
Yeah, but in the problem, they don't explicitly say mean virtual temperature, only the mean virtual temperature from 1,000 to 500.
Right, just from 1,000 to 500. So what we're doing is we're looking at just this section here. So take
I see what you're saying.
So do you have your calculator with you?
Yes.
I would just go, well, I can do it this way. 20.3 times 273. 5541. So you got 5536.8. So the question is, how did you get a different number? Maybe it was rounding. 29.26 times 273 times the natural log oops. Okay, hold on. Are you guys doing this with me?
Yeah.
No, oops. Hold on. 2 natural log times 29.26 divided by 273. I think I see the problem. I'm getting something really bad here. Natural log of 2 times 29.26 times 273. 5536. So why did you get 29.26? Do you see how annoying it is to grade high science?
RD over.
RD over G naught is 29.26, constant. Just right above.
I don't think. What's RD?
287. It was.
Oh, I didn't get 29. What value did you plug in for those? What do you plug in for G naught?
Probably 9.8.
When I do that, I get 29.285. So basically 29.29.
All right.
Again, I'm not saying that you did something wrong, but there might have been a rounding error here. So I'm just wondering where that number came from.
What do you do? 29.26.
Yeah.
If you plug in 9.81 instead of 9.8, you get the 29.26.
Oh,
Significant figures.
so this
Yeah.
is, I hate significant figures. Can I?
Yeah, I do too. Sorry. I
No,
got to
no,
drill
no,
in my.
that's okay.
That's what happens when you do an undergraduate in chemistry.
No, I get it. It totally makes sense. I'm just trying to find the values of this. Where did they first use that? Okay, and so the book, so my equation, what does my equation do? What's my equation been using? 20.3, which is what it is on page 69, 3.27. And 29.3 comes from R over G naught. So that must even be a bigger rounding. So not only did I get 29, you got 29.26, they rounded it so that they ended up on this number. So I guess the point is, guys, when I do problems and I'm looking at grading, do you realize how difficult it is based on the values just to see this number would be slightly different than my number because of the equation we use? So that's I want to underscore that kind of stuff. Now, significant digits, James and Nick, are you familiar with significant digits?
Yes, unfortunately.
Okay.
No.
The question is, well, what value would you use? What is the significant digits for how many do you want? And the answer is, well, I don't know.
Yeah.
But do you agree? And I want to make a little side point. If I used 29.87 or 29.876 or 66 or whatever I did, and I'm rounding it here, do you understand that the actual value may be this, but I'm rounding it to here, so I'm off by in the 100th or the 1000th place?
Mm-hmm.
This is where chaos theory in meteorology comes in, because you could run the same set of equations by changing it down to the third digit, 1000th place, and end up with completely different answers somewhere down the line in a forecast. And that's incredibly crazy.
It's also rounding bias comes into play too.
Yep. So all of that things in a model, in a non-linear system, this becomes bigger than the actual value. The error does. It explodes. So we have to be careful of those errors. But we also have to understand that there's uncertainty. It always is. Because a small change in the initial condition leads to incredible error growth at some finite point in time. Anyway, All right, so that's the one part of the problem. Let's look at the second part of the problem, which is this one here.
I have a question.
Yes.
Why in the second part are you allowed to use that temperature if it's not the mean virtual temperature?
Okay, and the answer is, well, you're kind of not. So what you could have done is look on page 70. Very last equation on page 70 is the full-fledged hypsometric equation. Obviously, when you're doing your notes and you're talking about the hypsometric, that's what you need to do. But when we go to the solution on this next page, and they say, I know the scale height, they come up with this simple relationship that the height at 1,000 millibars is about 8 times the surface pressure minus 1,000. Okay, so if I did that, then what I would be saying is, what is the height of 1,000 millibars? Because we're below sea level. Well, according to this equation, it's going to be 8 times the pressure at the surface. What the pressure at the surface is 1,020 millibars minus 1,000 millibars.
Is this equation true for all cases? Is this just like a regular equation?
Notice what they put here. It's about that.
Okay.
When you do that, 20 times 8, that's 160 meters. That is what they're saying. No, wait, is that what they're saying? What are they saying? And then there's, oh, here they're saying 50 meters below sea level. So I could take off 50 and I get 110 meters.
10, yeah.
Which you do down here, Jim.
Yeah, I did that in.
And what there's lots of little things that you can do. So Allison, let's look at your question. How true is this? How true is this? Well, let's take a look at an actual example in the atmosphere. Well, when I say actual example, I'm not saying an actual data, but let's think about what's going on in the atmosphere. So I've got the ground, and let's say that the temperature is 1,020 millibars at some virtual temperature. We are assuming in the atmosphere that the temperature profile is dry adiabatic and that the mixing ratio is well mixed. That we have a well mixed atmosphere. So there's your LCL. And I might be looking at some place about there. And so we already said this is around 110 meters. What is the difference in the temperature from there to there if the atmosphere is well mixed? If the atmosphere is well mixed, then the atmosphere is dry adiabatic.
Mm-hmm.
9.8 degrees Celsius. Let's just say 10 to make it easy. We're about 110 meters. So it should be at least 1 degree Kelvin. Right? What's the dew point going to be down? It goes down 2 degrees. So it's about 0.2. The dew point is about 0.2 kelvins. The mixing ratio is the same, so the virtual temperature correction would not be a whole lot different. So this really doesn't matter a whole lot for changing that virtual temperature if it's well mixed. Do you also remember in the atmosphere that the atmosphere has a skin moisture that usually looks something like this? If you look at soundings, you get what they call the skin vapor. You bring a lot of vapor into the air and it mixes up eventually, but you actually produce more vapor down here. So you can get dew points at the surface somewhere, maybe 80 degrees, let's say. You go up 100 meters, it's not 80 degrees. It drops considerably. That's a skin dew point. We're not worried about skin temperatures like this. I'm just saying, be aware of that.
How high does the skin boundary go?
Depends on the amount of vapor coming out of there.
Tens of meters, single digits meters?
Probably around 10 meters.
Okay, so it's real close.
It's pretty close.
Okay.
Right? Surface temperature, like temperature at the ground, is really hot.
Yeah.
That's why you measure things in the atmosphere 2 meters above the ground. You try to get past that. But if you look at our soundings, you'll see those forecast soundings showing that increase in everything. That's the skin.
Okay.
Okay, so in a hot, sunny day, that skin temperature is going to be considerably greater than on a cloudy day because the sun is doing the heating of that. Anyway, this is your change in the virtual temperature of about 1 Kelvin. So think about that just for a second. Okay, now I'm going to go back to this, and I'm going to say, all right, what did Jim do here? He says, well, I'm going to do this, and I'm going to take the temperature at 273. So he's saying that the mean virtual temperature is the surface virtual temperature. So Allison, that was your question, right? Well, can you use the surface temperature? And he got this. But do you understand that the temperature in that layer would have gone down by, let's say, 1 Kelvin? Which would do what to the virtual temperature? It would go down by half a degree.
Half a degree.
All right, so multiply 29.26 times 272.5 times the natural log of 2. So go ahead and do that and tell me what you get.
5527 or 5526.7.
5526.7.
Yeah.
Mm-hmm.
So according to this, it's about 10 meters different. And then the question is, well, how accurate do you need it to be? That's why we use, we say this is an approximation. The reality is it's not exactly. So a pilot's coming in and has to use an altimeter setting. And the question is, well, how close to the altimeter is that? And the altimeter is not going to have that kind of accuracy. It's not going to tell you 0 is 0. You're not going to be in the ground. You're going to be close to the ground. But a pilot goes, I know where the ground is. I can see the ground. If you have clouds over here, you have to have, what do you call this distance? That's the, so you're on the ground. This is the base of the clouds. What do you call that? That's called the
Ceiling.
Ceiling, right? And you have to have VV on a METAR. Do you remember what VV on a METAR is?
Vertical visibility.
Vertical visibility, right? You got to be able to see up and down. And there are threshold limits of when airports get shut down. Midway Airport gets shut down with what? I don't remember, what is it? 500 meter vertical visibility or something like that?
That sounds right.
Something along those lines. Now, can some airplanes land totally automatically without seeing anything at all?
Most.
Probably.
Yep, they can, but they're not using visuals. They're not using their altimeter. I think aren't they using some sort of a vertical like sonar or
No, it's a radio altimeter. You shoot
a radio altimeter? So you're hitting signal down and getting the return. You can measure that, so it's a lot more accurate. And that's what we're talking about. How accurate do you want to be? If we took the correction, it would be about 10 meters. That's if the temperature were dry adiabatic. So in the middle of the afternoon, you're going to be off by that much. At night, it may be an inversion, and you might have an isothermal atmosphere, and therefore it's fine. So this is sort of worst case scenario. The more, obviously, the bigger the layer, the greater the error is going to be. So that's why they say you can use that equation for x is much less than 1, and they show you mathematically why that is. So about, for every millibar drop, it's about 8 meters when you're near the ground. But that's, you got to be fairly near the ground. So your actual numbers, and again, this is just underscoring this point, the actual numbers you get for these answers can be off by some amount because of your assumptions that you make. Which equation are you using? Jim used this equation, and there is an error in that. If I use the equation Z equals 8 times the difference in pressure, I'm going to get a number that's off. But when you come right down to it, we were within 0.1 meter, depending on how we worked it out. It just kind of worked out that way. It's close enough for college level, undergraduate level science. But what's key about this problem? How's it going, James?
Well, it's going.
Are you following the discussions?
I am.
Okay. What's key about these problems is to understand how to use the hypsometric. And the hypsometric says you need the virtual temperature. You need the mean virtual temperature. Keep in mind, page 70, there's a graph that tells you how to calculate the mean virtual temperature of a layer visually. But it's got to use a log P. Logarithmic P on the side. Okay, next problem is we do 328.
Yes, that was one of the problems.
How'd you do on that one? Allison, this is what we talked about. 328 is what we talked about before you took that test.
I still haven't gotten what I got on my test back yet. He keeps pushing it off.
Well, that's because it's annoying to grade stuff like that.
Yeah, there was a similar question I almost wanted us to do, which was kind of similar to the last one we just did, except they didn't give us a second, or they didn't give us virtual temperature. So he wanted us to kind of figure out a way to solve for it.
And a lot of those are going to be like, yeah, you're getting the idea. Okay, so let's see what, so Nick, how did you do on this problem? Mike, how did you do on this problem?
Didn't find it. Looking for DU.
This is a, well, yeah, you don't want to use DU. What do you want to use instead?
DQ
No.
or DH.
Well, no. First law is DQ equals what? DU plus DW.
W.
So you want to use a better form rather than DU, so it's just CP dt. So let's see what you did. You said find the mass. Okay, so you solved and got mass. Okay, so you could do that, but I don't think that's the purpose of this problem. You didn't need to know the mass.
You could just solve for dq equals cp dt, right?
Okay, so let's go to the blank screen and let's see how this is. So what I have is I have a slab of air. And the slab of air, and again, I'm gonna draw this because I'll show you why we want to use a slab. Is being heated through the layer, which is Q in is 5 times 10 to the 6th, not joules. That's an amount. Joules per meter cubed, meter squared. So in other words, the heat is coming in, let's say, to the bottom of the slab. It's heated per meter squared, so it's per area. So this isn't just joules, it's joules per area. Now, if I knew the mass, if I knew that, then I would want joules per kilogram, which is usually how we deal with heating. This is joules per meter squared. It's a rate of heating. It's really a what? When you do it over per meter squared, what does that make it?
It's force.
No, when you have a heating through an area, that's a what? What's the word? And they do this for a reason, because this is how we kind of deal with stuff in meteorology. But what do we got? What is a heat through an area? You remember the term?
Oh, flux.
Was it?
It's a flux. You guys remember that?
Flux. Okay.
I do now.
Mm-hmm.
Think about what we talk about. We talk about a sensible heat flux. We talk about a radiant flux. Irradiance is a flux of energy per meter squared. That's why they're doing this. Because they're not saying, this isn't an isolated system where you're getting X amount of heat. You're getting a rate of flowing of heat. Now, we talk about flux in terms of irradiance. It's not joules per meter squared, it's watts per meter squared. What's the difference between a joule and a watt?
Watt includes time.
Watt includes time. A watt is a joule per second, right? So you have joules per second, which is going to be kind of a big deal, right? So hold on, I'm just stretching my legs because I got a cramp in my left hamstring.
So joules per second are pretty much just watts.
Yeah, joules per second's a watt. So watts per meter squared is just joules per meter squared per second. So that's a heat source through an area. But this is important because I don't have it per kilogram, which is what specific heat is, right? What's CP? What does CP stand for, first of all?
How much it takes to raise the temperature 1 degree?
Right, it's a specific heat, which is always given to you in joules per kilogram. But I'm not giving it per kilogram. So Jim, that's kind of what you thought. Well, I'll go figure this out. Okay, so I take the first law of thermodynamics in here, and I say, okay, let's write the first law. dq equals Cp dt. And again, Mike, this is your internal energy, because you're talking about a temperature change. And U is a function of T only. Remember we talked about that? Internal energy is a function of T only. Minus alpha dP. And what's the first thing that we can assume? That goes to 0.
That goes to zip.
Because there's no work being done. The assumption. But I want you to think about something, and this is what caused me to make this an 18-hour problem. Do you understand that they are saying this is 1,000 and this is 500 millibars? What's above this green slab? Isn't there another slab of air that goes from 500 to...
Yeah, the rest of the atmosphere.
If I heated this box and it expanded, which it would,
Right.
wouldn't it do work against 500 millibars of pressure?
Yes.
Isn't that work?
Yes.
Mm-hmm.
So is that 0?
No.
Try to solve the problem by not calling it 0. You don't have enough information.
Yeah.
They assume it's 0.
Can't get there from here.
Annoying! Okay, so anyway, that's all I'm saying. Okay, so I'm now going to write this equation. dq equals Cp dt times the number of kilograms. So in other words, and I'm just going to do this in here, it's times mass. Because a lot of times I go, per unit mass. Well, I've got a lot of mass. So the question is, I kind of need to know the mass of this atmosphere, of this big slab. And what you did is you did some stuff where you said this is how many kilograms it is. But I don't need to do that because the change in pressure from the bottom to the top is, if pressure is the weight of the air above you, do you understand that the pressure has changed by 500 millibars? That's the change in the pressure. But pressure is force over area, which is equal to mass times gravity over area. Right? But I have heating going on in units of joules per area. And I know the pressure, which is mass over area. And I know the pressure, and the only thing I'm missing from this equation is gravity. So I can look at this and go dq over area, which is what I'm given, is equal to Cp dt times the change in pressure over gravity. Because mass, and here I'll show it to you in better circumstance. Mass is going to be the pressure times the area divided by gravity. And when I plug that into here, and I know the pressure is the delta pressure, 500 millibars worth, I bring the area to the left side and I have the gravity on the right side. And all I need is a change in pressure. Notice there's no mass term in here at all. So there's my equation that I want to have. I know what this is, right? So I'm gonna, because I'm not doing it really neatly and I don't want to erase anything, I just want you to know that that is this. What's CP?
1,004 joules per Kelvin kilogram.
So you're asserting that dq over area is equal to qn.
Say that again.
You're saying dq over area is equal to qn.
Yes, that's what they're giving it to you. They're not giving it to you in terms of just pure heat. They're not telling you how much. They're giving you a kind of a flux without a flux of heat.
Got it.
And then I know dP is what? It's 500 millibars, but I don't want to do that. I want to do 5 times 10 to the 4th pascals.
Right.
Because I care. And I know gravity is 9.8 times 10 to the minus second meters. Oh, sorry.
Okay, so hold on, let's. Divided by. Okay, so I get.
What do you get now? Now, James, so you could do this, right? You could calculate this.
Yeah, that one is definitely, I think, the easiest one.
Same answer.
And you get, right? Equals 0.976.
Yep, that's what I got.
Mm-hmm.
But notice, I don't have to explicitly solve for the mass, and that's what you did.
Yeah. Almost make me want to go back and do all these problems, but do them a different way.
So I think that's kind of cool, right? So you get a delta T.
Yeah.
Now, I want to show you, because it's not the whole of the problem. Any questions on this? So you see, Allison, how we did, because when we talked that problem that you did for your class, that same thing where mass over area is stuff that you have times gravity, and then you start going, well, that's what pressure is all about. So it's seeing those little tricks that you do things like this. And again, it just comes from experience. So here, let's try this. So I know that dt is 0.976 kelvins. Okay, so what I'm looking at, delta Z is equal to, because it's 1,000 to 500 millibar thickness, 20.3 times the mean virtual temperature. Do you agree with that? And delta Z is thickness.
Right.
And what is thickness? Two-word answer. What is thickness?
Geopotential height?
No, it's not a height. It is a
vertical distance.
Right? It's a vertical distance between the isobaric surfaces. So what is this? What would that expression be?
Second derivative.
Yeah, but how would you just say what this is?
The change in thickness?
The change in the thickness. Do you agree that by heating that air, you're going to change
Oh,
the layer?
I see what you're saying.
So the change is
So
going to be 20.3 times the change in the virtual temperature. Well, you already said what's the average temperature change of that layer. So that means the change in the thickness is going to be 20.3 times 0.976, which is what number?
19.81.
Right? There's your thickness change. When I heat a layer of atmosphere, I'm going to cause expansion of that atmosphere. You know, when you see the problems, don't they kind of seem easier than you think they are?
Yep.
It's just finding a good foothold to start in.
Yep.
Right? That's the hard part.
And flipping through your book to find all the equations you need or through all your notes.
Well, once again, this is the Hicks metric. But what's really important for me, what's really important for me to tell you guys, James, is that you want to think about what's going on. So imagine this. I've got a layer of atmosphere that's being heated through some flux of heat. Sensible heat flux, radiant flux, whatever you want to imagine it. That anytime you heat the atmosphere, it's going to expand that 2,000 to 500 millibar layer, and I can calculate the height, the thickness change. That's what you just did. But that's not the way you would do real meteorology if you're doing forecasting. You'd say, my thicknesses are changing. What's the reason for it? Now, what's another way you could have heated? So let's just talk for a second. I have 1,000 to 500 millibars. So we'll go 1,000, 500 millibars. How do I heat this layer of atmosphere? What are the three methods of heating the air?
Conduction, convection, radiation.
Now, if I were heating this layer of air by radiation, where would the radiation be coming from?
The
Top down.
sun.
Are you telling me it's from the sun?
Or the clouds.
Or the clouds.
Or the atmosphere above it.
Well, yeah, hold on, right? The sun is not going to be an effective heater of this layer of atmosphere. The sun does not cause the thickness of the atmosphere to change very much because most of it's transparent. About 50% gets through, about 30% is reflected. I've only got 20% left that might be absorbed. I'm absorbing a lot in the stratosphere. So the sun has a role, but it's secondary.
Secondary.
This part of the air can heat the atmosphere. Certainly can. The ground certainly heats the atmosphere, but how will the ground heat the atmosphere would depend upon the distribution of what?
Water vapor?
Right? Well, simply greenhouse gases.
Oh, okay.
Carbon dioxide, you would assume, is fairly all the same throughout this layer. I mean, there might be some variations. I mean, there certainly are variations, but ish. But what's the really big difference in this?
Water vapor.
Right? H2O is going to be highly variable. So the presence of water vapor in the air, absorbing infrared radiation from a warm ground, what part of the atmosphere should expand more? Or should be warm? Close to the ground, because there's a higher distribution. What will that do to the lapse rates of the atmosphere, therefore?
Increase.
Right. So in other words, water vapor is actually, water vapor and being heated by the ground is a destabilizing influence. Right? Mind-boggling.
Well, it's kind of common sense once you break it down.
Once you think about it,
Yes,
well, okay,
yes,
it makes sense, right? Yeah, and that's, but if you don't ever stop to think about it,
yes.
it's like, oh, I wouldn't have known that. Okay, so that's all beautiful. How else could I heat this? Now, you said conduction, didn't you?
Yep.
Okay, well, where does conduction work?
Adjacents.
The conduction is only working here,
Yeah.
okay? Into what is this layer called?
Boundary layer.
Not, the conduction itself is only happening where?
On the ground.
Oh, the molecular
Boundary level.
boundary layer.
Only at like a centimeter. But do you understand that that air will then mix up? And that will mix up to the top of the PBL. And actually, people would say that's the top of the CBL. What does CBL stand for? CBL is probably how most people would reference this in this event. What's CBL stand for?
Convective?
Yeah, Nick, your mic's not working again. Convective boundary layer.
Convective
Yeah.
boundary.
Oh, there you go. That's much better. Convective boundary layer. And that's because what dominates the convective boundary layer? What
Eddy?
eddies, right?
That is.
What are the two types of eddies?
Upward and downward?
No, you remember the two types of,
Oh.
they're turbulent eddies, first of all. What are the two basic types?
Oh, thermal.
Right, thermally induced. Thermally is because you're heating the air, and those are much bigger. Mechanically induced is wind flowing over the ground. Those eddies are mixing up the atmosphere, and they're redistributing the heat. And so what part of the atmosphere are they going to cause expansion of most of all? Down close to the ground. Maybe 1.5 kilometers, 2 kilometers in the hot, dry air. But that expansion will also cause the rest of the atmosphere to expand. Your thicknesses should go up when it's sunny. That is the heating term. But that is still not 1,000 to 500 millibar thickness. So what's going to heat this part of the atmosphere the most? Allison, you're muted. I didn't hear you. Oh, your mic's not working. What do you think will heat this part of the atmosphere the most?
Action.
Maybe some of it. But remember, the convective boundary layer is down here. I want to go up here.
Oh, latent heat.
Latent heat release.
Latent heat release is a huge generator of expansion of the atmosphere. So imagine that I had a big layer, and this is not necessarily convective clouds. I don't want you to think always thunderstorms, although thunderstorms are a big player in this. If I have a big stratus deck, and I keep getting advection of warm air or something, do you agree that maybe this will be, it could start as snow, but if I have clouds going on for a long time, even without warm advection, I mean, I guess warm advection makes it, I could expand the layer enough to warm it enough by latent heat release that I start getting melting. So snow becomes rain. So all of those things are heating layers of the atmosphere. What about above 500 millibars? What heats air up there? I mean, you could have some clouds, but you agree that the clouds are probably going to be a little bit less. But in this point, out here, these clouds are going to do a lot of heating out here. That changes the thickness. And what do we call that? What's DMC stand for?
Deep moisture convection.
Deep moisture convection, right? Big thunderstorms are now going to go well through that layer, much higher. I can also heat the air.
So those would that would be associated with CVs.
Yep.
Okay.
But I can also heat the air from bringing air from what layer?
Troposphere,
No,
Stratosphere.
stratosphere down.
stratosphere down, called stratospheric folding, where I'm bringing some of that air. Because remember, the temperature is stabilized. We have theta values go really high up there. So if I bring that air down by mixing from the stratosphere down, I'm actually providing a heat source for the upper atmosphere.
What's the mechanism by which that happens? Sorry.
Ageostrophic jet streak.
Okay, so it has to do with the jets.
And really, yeah. I mean, and there's the other, and I would teach you it if I could, but I don't know it well enough.
I'm just curious.
But I want to show you one thing in here that I've probably never told you. So I'm going to look at the GFS, and I'm going to look at something here called the dynamic tropopause, which is called potential vorticity units. And these potential vorticity units, because vorticity will cause that vertical accelerations, will bring stratospheric air down.
Now, when you say vertical accelerations, do you imply down or up or both?
Probably both, because you can go, counter.
Right.
But when we see these areas of strong PV anomalies that they call them, like this area here, so go to 138, what I'm going to see at 138 hours
Hello.
is, well, I start seeing cyclogenesis. This is past 138 hours for obvious reasons. That tells me cyclogenesis. So if I see big areas of PV anomalies, I'm going to get cyclogenesis. Now, look at, by the way, again, I don't know this really well, but do you see I have these oranges?
Yeah.
Stratospheric air. Well, it's not a coincidence that when I go to our satellite page and I go to air mass, I see oranges, because the orange is a result of ozone, and ozone implies that I'm bringing stratospheric air
Down.
So here, if I go ozone, you'll see, again, this is harder to see because there's other things influencing it, but I've got this area here of ozone, and I don't use ozone directly, but I do use it in the air mass calculations. So if I go to the product description, it says the red channel is the difference between bands 8 and 10, which is water vapor. Green is the difference of bands 12 and 13. There's your clean IR. And if I have red and green, what do I get?
Blue?
No, red and green combined? What color?
Red and green. Orange? No.
Red and green is yellow.
No.
Red and green is yellow.
Red and green is yellow. And if I've got red and green, yellow, and I've got big difference in water vapor, hence drier air, I will have red, and red and yellow make orange, and that's where the oranges come from.
Given between the time you saw that jet and the cyclogenesis, does that vertical acceleration initiate cyclogenesis, or should it be seen as a correlation?
that's a decent question, and I'm not going to tell you that I know this for sure, but I would say it's a better correlation.
Okay.
When I, like over there at 57 hours, I see areas where I should be thinking cyclones.
Okay.
At 69 hours. So let's go to the surface products. Let's look at the temperatures. 59 hours. I see cyclogenesis. Oops. In that time frame over here. And I see, well, high pressure is coming in after that time. So where is it ahead of time? There's this cyclone.
Okay.
So I don't use this very often in the dynamic troposphere because, again, I know it enough to be dangerous, but not enough to explain it. I'm not level 3. So if it says potential vorticity is the product of absolute vorticity and stability, regions of high stability, such as the stratosphere, or high absolute vorticity along the trough axis, are characterized by high values. There's an inverse relationship between tropopause height and pressure on the dynamic tropopause. High pressure on the dynamic tropopause corresponds to upper level troughs, low tropopause, and positive upper level PV anomalies. So remember, the higher the pressure, the deeper the upper level trough. So, yeah. So in here, what we're saying in the orange is that the pressures of the tropopause are going to come down. And if you've got that air sinking into that high part of the atmosphere, it's because you've stratospheric air in a part of the atmosphere where now you've got warmer, stable, heating air. So this goes into a little bit higher levels of advanced dynamics, and I don't have the skills on this stuff. Like I said, I know it at about a level 1, maybe to level 2, but I can't really teach it. I don't feel comfortable. But at least I wanted to show you why this matters, because when we started looking at heating of a layer of atmosphere, it affects things. Now, something I don't...
How does that compare to the upper jet stream? Can we look at that compared to 250?
Okay, so it's 69 hours here, Mike, right? We've got those 2 regions of PV anomalies. We have these big upper level troughs. So when I go to wind speed at those time frames, 69 hours, right? I'm seeing a digging trough. There's a significant shortwave probably here, and there's another shortwave over here. So if I go to 500 millibar vorticity at that time frame, there's a digging trough out here. And
so they mirror each other.
Yeah, they'll be related because these things come about in synoptics. And synoptic meteorology has a lot more influence. I mean, there's a lot of things to deal with. A good advanced synoptics class will teach you that. It seems to me that like most undergraduate synoptics class are still dealing with geostrophic winds and gradient winds and all that other stuff. An advanced synoptics would deal with this kind of stuff, PV anomalies. Lance Bozard from NYU, or no, State University of New York, Albany, is really a big name in this. So there it is. I'm throwing it out there. Live it, love it, whatever. Now, because you guys are not in my classes, I wanted to show you something. I don't know if you've seen this, but there's some really cool things that we've got going on here. We've got temperatures on a model, right? Hold on, what's today's date?
Wait a second.
So I'm going to do that first, and then I'm going to go to here just for a second. I'm going to go to 850 temperature anomalies. Now, actually, let's go to surface temperature anomalies. So one of the things that we are doing is we are changing just our perspective and looking at how it compares to long-term anomalies. So here's surface temperature anomalies. These are actual values of surface temperatures from last night's 0Z run. So let's just go here for a second.
Is over hours or days?
Oh. This is a model product, so this
Okay,
is
okay, so you're doing it over.
These are actually temperatures in the upper Midwest, and in, you know, this is at 69 hours, or it's getting to that place where we've got this extreme cold coming in ahead of this. So the trough is going to be here, and you're going to bring in this cold. It's 30 to 40 plus degrees below normal surface temperatures. You're down over here, Allison, you're a couple degrees below normal. Look at that cold air that's building in. That's brutal. That's winter.
Oof.
Yeah, that's snow.
We're lucky because we're not too bad, but if you look at the cold anomalies, that's the cold front. That's a blue norther. And then it comes down pretty good to the south, and it comes across, so that Texas is now going to be 20 to 25 to 30 degrees below normal. Luckily, there's warming behind it, so it's not too ridiculous yet.
That happened in January, it'd be awful cold.
Oh, it'd be awful cold. And then we get this big warm up late in the period. So as we go into the first weekend of November, our temperatures are actually going to be above normal by, I don't know, in Illinois, 10 degrees above normal highs. So it might be 60.
So this is the GFS.
I don't see, and this is the GFS, but you know, there it is. There's an anomaly. And if I do that with, I don't want just anomalies, but I want to go surface temperature standard anomalies. So I want to look at standard deviation to see how far in terms of standard deviation below normal we are. We've got down into the Texas area, we're down at 5 standard deviations below normal. This is a big cold outbreak coming.
Bring it on.
Right, that's cold outbreak. Now, we're about 2 standard, so it's a little bit below normal, but that is huge for the panhandle.
Whew.
And the cold is not as bad along the southeast as it had been. But you notice, as we go forward, it's not that cold. And then we go into a pattern shift where the warm air starts taking over, and now we're actually going to be a little bit above normal, not so much. So if I go to climate and I look at our temperature outlook, notice that we have this significant temperature outlook. And then on the 8 to 14 day, it's not as severe, not as significant. Still warm out west, still fire season, still warm out here. So no end in sight. Drier than normal, dry. So we have this area where it's going to be 30 degrees below normal with precipitation. You know, there'll probably be snow down into Kansas, maybe even in Oklahoma. If I look at last night's 0Z and I look at precipitation type, there's a big snowstorm coming into Colorado. Those isobars are packed. 1040 millibar high. That's a big snow event into Colorado. Snow, freezing rain, sleet into the Texas Panhandle for this early next week. I mean, even down to San Antonio, there's a possibility that you might see some wintry mix. I mean, that's crazy, isn't it?
Mm-hmm. Wow.
How much snow in a perfect world? I mean, really? I'm looking at areas of Oklahoma and Texas Panhandle at 10 inches of snow.
That's
Oh,
I mean, I'm seeing snowflakes down to the Rio Grande.
In October?
In October.
Oh,
Big snow across here.
Wow.
Luckily, we're not, so the southeast keeps us warm.
We
But
gotta
then,
beat 'em.
when you start looking at 24-hour snowfall accumulations, we go later in the period and all of a sudden the snow ends. So it's not winter yet. All this snow will melt. But that's a lot of snow in Colorado.
for this weekend.
Yeah, from Sunday to Monday. So again, if we go to our text page and we go to winter and we look at probabilities, on day 3, we start seeing some high probabilities of snow up north. We don't go beyond that, but there will be stuff coming on this weekend. All right, what's the next problem?
cool.
You guys mind that we go into weather every once in a while?
No.
It's fine. 3.32.
3.32, how's that one? That's easy?
That one I thought was the easiest.
Oh, yeah, that's, I think that one's an easy, I'm in fact, it's so easy, I'm just going to use one of your guys. Nick, you did this one, so let's go to yours.
Yeah.
I think this is why I hate grading. When I have to load a grade and I have to sit here for 15 seconds, I get distracted. Oh, how's it going, James?
Oh, it's going. I am. Cold weather is gonna be pretty great. I am definitely able to handle that better than like.
You're a cold weather guy?
I got the cold weather blood. Yeah, I got it from my mom's side of the family. My dad and my sister are already like wearing these giant sweaters, so they're the me and my mom were walking around in t-shirts still.
So did you get this one right, Nick?
No, I wasn't really thinking about the
Okay.
it being a heat source per area.
Ooh,
So.
3 point.
Okay, so basically you were looking at isothermally, so we go P equals rho RT,
Yeah.
and we go 1/10 of its volume, so we know the mass,
Mm-hmm.
but we'd really use P equals MRT, or right?
I used raw RT in this case.
Which is fine, mass over volume.
Yeah.
We know we know 2 kilograms. We know the volume is just 1/10,
Mm-hmm.
and you know it's compressed at 15 degrees Celsius. So really, what equation really should you be using though? What's the easiest equation to use? Hey, can you hold on for a second?
Sure.
Now, Rantoul. Who's calling me from Rantoul? They can leave a message. Who do I know in Rantoul?
I got a call from Connecticut a little while ago. I don't know anybody from Connecticut.
and new Air Force bases in Rantoul, right?
You know what it used to be?
Not anymore.
It's not there anymore.
The remnants of it.
Just a museum and an industrial park, research industrial park.
Air Force still there, I think.
What I would have done is I would have used this equation,
Yeah, that's what I used.
Mm-hmm.
right?
Yeah.
So on page 95, take a look at page 95. And I would have used actually Right. What would I have used?
I use delta W equal to the negative integral of 2r dt over v dv.
Yeah, and the reason that you can do that is, hold on a second. I don't want to say the wrong thing.
Because v1 is equal to v2. Or v1 is greater than v2. I think that's the reason you can do it.
Yeah, I think what it is. Did it say, yeah, so here's how I would have set the problem up. So here's how I did set the problem up. I say the total work is equal to of PdV, right?
Yep.
And P equals RT over V. I could have used alpha, and alpha assumes what?
Unit mass.
Right? So since I have 2 kilograms, I'm going to multiply by 2 eventually. But I'm doing it per kilogram, so I could write it in this form. And so instead of V, I'm going to use alpha. So I can go alpha 1, alpha 2, RT d alpha over alpha. But I know R is a constant. R goes out. T goes out. And I'm left with RT integrating alpha 1, alpha 2, d alpha over alpha, which is pretty straightforward. RT, the natural log of alpha. I won't mess you up. Of alpha integrated from alpha 1 to alpha 2, but that's equal to RT times the natural log of alpha 2 minus the natural log of alpha 1. But the rule of log says it's RT natural log of alpha 2 over alpha 1. But alpha 2 over alpha 1 is 1/10. Right? You're compressing it to 1/10. So that just becomes RT times the natural log of 0.1. Plug in the values, and what do you get?
The answer.
I'm gonna let you do, but you get positive or negative?
Negative.
Negative.
Why do you know it's negative? Because it's the natural log of
Being
0.1,
done.
which is a negative value. 1
And that
times 10 to the 5th. But I'm doing it times 2 kilograms. That's because that was per kilogram. That's
Right.
work per kilogram.
Right.
And that's a pretty straightforward one. Okay. Now, we have a couple more problems, but we're almost done. So since your assignment was to have them done, oh, I still haven't given you that thing.
Right.
So, shoot, I meant to do that. I have to go on another computer and download the files, so that's a problem.
Yeah.
So I will do that this weekend, promise.
I still technically did that correctly. I think I got pretty much the same answer.
Yes, you do. And there's multiple ways of doing it.
Exactly,
right?
yeah.
You got to see that there's always multiple ways.
Mhm.
How many more problems are there?
We did the
Three.
we did 3.33 already in class, right?
Yes.
1, 2, 3, 4, 5.
Okay, so we'll work those out. So Now, I know some of you have to turn in the rest of your stuff, or you might want to go back and make them better, which go ahead and do that. James,
Yes.
no more of being late. But what I want you to do is, because I'm going to give you an assignment for Tuesday, is I want you to read chapter 7. Let's just have you read section 7.1. Take notes on that. It's only like 5 pages,
All
but
right.
it's hellacious pages.
7.1 by Tuesday.
Oh, kinematics.
And that's what we want you to do. So we're going to have some nice discussions on this. But once we're all ready to go without these problems, I'm going to start bringing into matrices and Calc 4 stuff and all this other cool stuff and show you how it works. That's where I really like the dynamics part of this stuff. So that help you, Allison? Okay, so you got to see these things. All right, guys, have a good weekend. Enjoy your warmth while it lasts, Allison. Same with everybody else here. We'll see you guys on Tuesday.
Right,
Yeah,
have a
Tuesday.
good weekend. Bye.
Have a good weekend.